So what is the weight of an object? It's the force of gravity with which the planet, in this case our Earth, pulls the object towards itself. Consider a box sitting peacefully on the floor. Since the force of gravity acts on all particles of the box, I am going to draw the force of gravity from the center of the box. Now, if you remember, Newton gave us a formula for that. G, mass of one object, mass of the other object, divided by square of the distance between the two. But then you have to remember that this formula applies only to point particles. When you have 2 point particles, the distance between them is clearly defined. No problem. So we can simply write mass of particle 1, m1, mass of particle 2, m2, divided by square of the distance between the two, and that's the distance between the two. But what happens if you have two extended objects? For example, supposing I have this asteroid 1 and let's say asteroid 2. Well, you will say, cool, let's write down the force on asteroid 2. It's going to be mass m1 of asteroid 1 multiplied by mass m2 of asteroid 2 divided by, and at this point you get stuck because you will now realize that there are an infinite number of pairs of points between which the distances are different and you don't know which distance to take. You see, before I proceed further, I know what you're thinking. You're thinking about the centers of mass, but before I get there, I just want to point out something very interesting. That is, distance between two extended objects cannot be defined. We can define distance between 2 points, but not between two extended objects. We can't define the distance between two extended objects unless, of course, the two objects are so far apart that their sizes are negligible compared to the distance between the two, in which case we can treat them to a good approximation as point particles. And you can take the distance from any point on one object and any point on the other object and use the formula gm1 m2 by r squared. But when you have two extended objects fairly nearby, there is no concept of a distance between extended objects. You will then say, why don't you take the two centers of mass? Let's take the center of mass here and center of mass there. No problem. Then, of course, you're defining once again the distance between 2 points. All right. Now, let's see if this is valid. Supposing I take the entire mass of asteroid 1 as being located here, and the entire mass of asteroid 2 as being located there, and I take the distance between the centers of the mass, and I use this formula, will I get the correct answer? I will now show you that it won't. So, to illustrate that, what I'm going to do is take the simplest extended object that I can think of, a massless rod connecting 2 point particles. Here's 1 point particle and here's another point particle. Let's say this one has a mass m. Oh, let's make it just m and m, not m1 and m2. Make it simple. Let's say m and m separated by a rod of distance of length L, and along the straight same rod, if I extend the line, at this point I'm going to put another mass, capital M. I'm going to ask the question, what is the force exerted by this simple extended object on this point particle? We know that Newton's law of gravity can be used for point particles. And so we'll treat this extended object as being made up of 2 point particles, and due to the one on the right, the force is going to be G m m divided by the distance between the two. Let's take that as d. So d squared. And what's the direction of the force? To the left. It's an attractive force. What about this point particle on the left? That being further away will exert a smaller force but in the same direction, and that's going to be G m m by L plus d the whole square. Since the two forces point in the same direction, we can add their magnitudes. So this is the force of attraction due to the extended object on this point particle. What would have happened if I had treated it as one single point particle located at its center of mass? That is, I take this extended object and assume that the entire mass can be concentrated at the center, and that mass is 2m. And what will be the force? It will be G 2m m divided by square of the distance L by 2 plus d the whole square. This is not equal to that. In fact, to make your calculation simple, why don't you take d equal to L? Check it out. This will not work out. That tells you treating the entire mass as being located at the center of mass gives us the wrong answer. This is the correct answer. Let's go back to our asteroids now. Here is asteroid 1. Let me draw it again. And here is asteroid 2. How then do we find the force exerted by asteroid 1 on asteroid? Since we are allowed to use gm1 m2 by r square only for point particles, we have to divide up the asteroids into point particles. So let's take one point on asteroid 2 and find the force on it due to all the point particles of asteroid 1. So you're going to get a force in that direction due to that distance. You're going to get a force in that direction due to that distance. You're going to get a force in that direction due to that distance, and so on and so forth. And you're going to end up with, let's say, if asteroid 1 is made up of 10 power 28 particles, you're going to end up with 10 power 28 vectors. And you'll have to take the vector sum of all these 10 power 28 vectors, and you end up with the force exerted by asteroid 1 on one particle of asteroid. Now go to the next particle in asteroid 2, repeat the procedure. So the first net force on particle 2 might have turned out to be that vector. When you repeat the procedure on another particle, it may turn out to be this, and so forth. On this particle, it may turn out to be some other vector. So you do it for all the particles of asteroid 2, and maybe there are 10 power 27 of those particles. And what do? You get 10 power 27 vectors, each vector being the sum of 10 power 28 vectors. And so totally you have 10 power 28 multiplied by 10 power 27 vectors. So once you get all the forces on each of the particles of asteroid 2, now you take one more vector sum of all these vectors, and that will give you the final force exerted by asteroid 1 on asteroid 2. Now you see, the number of vectors that we have here is about, let's say 28 plus 27, what's that, 55? So 10 power 55 vectors. So you can do a simple back of the envelope calculation, which I'm not going to do now. And you will see that it will take several lifetimes of the universe to calculate this, even if you have a computer the size of a galaxy. So what do scientists at ISRO and NASA, what do they do? How do they find forces between, let us say, two asteroids? Well, they're not going to take every particle on 1 and every particle on 2. Asteroid 2, for example, they might divide it up into, let's say, 10 million pieces. Asteroid 1 may be another 10 million pieces, that is 10 power 7 and 10 power 7. You get 10 power 14 vectors, which is much more manageable, and they will use a computer to calculate the force. And what you get is an excellent approximation to the actual force. Let's get back to our box sitting on the floor. So, what do? We need to take the Earth, and then what do we do with the Earth? We have to take every particle on the Earth and every particle on this box and calculate it? No. Luckily, we don't need to do that, because something new comes to our rescue. And what is that? That's called Gauss's theorem. Now you're going to learn about this theorem in class 12, right? I'm just going to give you the gist of this theorem, This theorem says that if you have two objects which have spherical symmetry, that's a fancy way of saying, supposing the two objects are perfect spheres, then you can go ahead and treat each of them as though the entire mass is located at its center. And so you can simply use center to center distance and use the formula G m1 m2 divided by r squared. R is the distance between the two centers. Now take this for granted. So now when we come to our box which is sitting on the earth, let us start by drawing the earth, and I'm going to draw the box. Of course, it is not drawn to scale. I'm going to also separate the box and place it there. Now it's clearly not drawn to scale because you can see the size of the box is almost the size of India. But in order for you to see it, otherwise you'll see it only as a dot. So now we can see how to use this. We can think of this box as a point particle in comparison to the Earth. The Earth's radius is 6,400 kilometers and the box is what? At most half a meter each side. So it's like a point particle, and we can simply take the distance from the center of the Earth to the box. Let me write that down. G, mass of the Earth, mass of the box, divided by radius of the Earth plus the height of the box above the surface of the Earth. Let's say the box is sitting on the floor of the second floor of a building, right? So it's at a height h, the whole square. Now, remember the radius of the Earth is 6,400 kilometers, and even Burj Khalifa has got a height that is completely negligible compared to the radius of the Earth. In fact, even if I shoot a bullet upwards, when I'm talking about projectile motion, even when I shoot a bullet upwards, the bullet may go up 1 kilometer or not even 2, maybe 1.5 kilometers, but that's nothing in comparison to the radius of the Earth. So we can neglect this height and put it equal to 0 for terrestrial problems. Of course, I cannot do that when I'm talking about a satellite which is in orbit around the Earth. So for terrestrial problems, the formula reduces to G, mass of the Earth, divided by radius of the Earth squared, multiplied by the mass of the box. This is the weight of the box. Supposing I wanted the weight of the physics teacher, what would I do? I would write down G, mass of the Earth, divided by square of the radius of the Earth, multiplied by mass of the physics teacher. In my case, it's 85 kilograms. I'd put that there. Or if I wanted the mass of this pen, which may be 20 grams, what would I do? I would put G, mass of the Earth, divided by radius of the Earth squared, multiplied by 0.02 kilograms. So each time I'd have to do the calculation all over again. So the clever thing to do is first pre-calculate this number, and then all I have to do is multiply the mass of any object by this number to get its weight. Let's do a rough calculation. G, Newton's universal constant, is about 6 into 10 power minus 11. Mass of the Earth is approximately 6 into 10 power 24. I'm going to do a very approximate calculation. Divided by radius of the Earth, that is 6,400 kilometers. So that is 6.4 into 10 power 3 kilometers. That becomes 10 power 6 meters. Don't forget, we got to square that. So let's do a very rough calculation. 6 times 6 will cancel with 6.4 squared. And I end up with 10 power 12 in the denominator, which goes into 10 power 24 gives me 10 power 12. 10 power 12 into 10 power minus 11 gives me 10. If I had done this calculation carefully, I would have gotten 9.8 as the answer in SI units. So I just have to multiply the mass of any object by this number 9.8 to get the weight of the object. From now onwards, we're going to take the number as 10. And this number, this in the brackets, this stuff, we're going to give it a name. We're going to call it G. So the weight of an object is written as m times g. And what you've learned today is something very interesting. If I ask you to calculate the weight of the object on Mars, what will you do? All you have to do is multiply m by this number g. This number g can be simply calculated on any planet as Newton's constant multiplied by mass of the planet divided by square of the radius of the planet. For example, if I do this for the moon, I get g as approximately 10 divided by 6. The weight of an object on the moon is going to be about 1/6 the weight on the earth. Of course, the mass will be the same. So now we are ready to get back to our original problem. So the force of gravity, we are now ready to write, which is the weight of the object, points downwards, and its value is mg. If mass is equal to 2 kilograms, then the weight is m times g, which is 10 approximately. So that is 20 newtons. That's the force of gravity. Now there's one more thing I need to tell you. If I pick up this object and simply drop it from a certain height, right? If I simply drop it and if I ignore air friction, the only force acting on it is that of gravity, and I should equate it to mass times acceleration according to Newton's law, according to Newton's second law. So m cancels and I get g is equal to a. So we find that the acceleration due to gravity is 9.8 meters per second squared, or we are going to use it as 10 meters per second squared. So this g is often called the acceleration due to gravity. Notice something very interesting about this acceleration. The mass cancels, which means that it's independent of the mass of the object. And this fact was discovered by not Newton, Galileo. Galileo said that if you go to the top of the Leaning Tower of Pisa, and from the top of which if you dropped a cannonball and a feather, they will drop together if there is no air friction.